Thank you, Maciek. Thank you, everyone, for coming. Thanks the organizing committee for allowing me to speak here. So, in this talk, I will talk about some joint work with my co-advisor, Charlotte Ardouin, on the topic of enumerating walks in the quadrant. So, without further ado, I will introduce the object. So, you are given some finite set of vectors in Z2, and what you do is you perform a walk in the quadrant using the steps that are in this set, which we call a model of walk, meaning that you are not allowed to cross the axis at all times. You must remain in the quadrant. So to such a walk, you may have some statistics. Here I show you n to be the number of steps the walk uses, and we also account for the ending point. So here the walk terminates at the point 30. And so the natural question is to determine the number qijn of such walk using n steps terminating at a given point. So in enumerative combinatorics, the natural thing to do is to just plug this number into their generating function, qxy, where the variables xy they account for the ending point, and the variable t accounts for the number of steps. So I will show you to derive a functional equation for such walks for this specific model, which will be our running example. So it looks like this, and I will explain each part. So you perform an induction on the number of steps the walk uses. So this term here, it's the starting point of the walk at coordinates 0, 0. And then for each step, I will ask myself to which kind of walk can I append it so I don't leave the quadrant. So I do the first one corresponding to this monomial. So you see that if you add this step to any walk in the quadrant, then you will still remain in the quadrant. So you multiply the monomial t x squared y by the full generating series q xy. So you perform the same argument for these two steps. And now you have a step which is a bit more interesting, because you see that if you end on the x-axis, you are not allowed to perform it, otherwise you will leave the quadrant. Hence, instead of multiplying by the full generating function, you multiply by the generating function of walks not ending on the x-axis, corresponding to this term. And you perform the same argument for the last step. Now, what we do is we regroup the terms in qxy to the left of the equation and put the remaining on the right-hand side. So on the left, the generating function qxy has a polynomial kxy as a factor, and on the right-hand side, you see that the terms qx0, q00, q0y, they are what we call specializations of the generating series. So in general, when you count walks in the quadrant, the functional equation for the generating function qxy will have this shape. So these kinds of equations, they are called equations in catalytic variables. Here there are two catalytic variables that are x and y, and in general, we don't know how to solve such equations. It is really difficult. Hence, instead of just trying to count qijn for a given model of walks, we want to see which models are hard and which models are easy, which models are hard and which models are easy, according to some hierarchy on formal power series, which is defined as follows. So at the bottom, the simplest kind of generating series that you can have are the rational power series. Higher in the hierarchy are the algebraic power series that are solutions of polynomial equations. And higher are definite power series that are solutions to linear differential equations with coefficients in the rational power series. And so I will show you an example. So these classes are interesting because if you know that your generating series is in one of these slots, then you have efficient algorithm to deal with the coefficients, to compute recurrence relation, etc., etc. As an example, I show you what has been done and completed in 2018 for the small steps, which are models of works that corresponds to this kind of, which are small in this set. We perform some enumerative combinatorics to eliminate the trivial cases, regroup them by symmetries, etc. And you find that 4 of these models give algebraic generating functions. These are these 4 ones. 19 are definite. I showed you one as an example. And all the remaining models are non-definite, not solutions to any differential equation. So they are really hard. And well, since we don't have a generic way to deal with such functional equations, it required a lot of different mathematical techniques, from combinatorics to difference Galois theory. And following the success of this first classification, we want to extend it to other families of models of works. And in this talk, I will focus on works with large steps, and more precisely, on how to perform the proofs of algebraicity. So, recall that in general, when studying such works, we had catalytic equations in 2 catalytic variables, and I said that these were horrible to solve. But we can do something if we only have 1 catalytic variable in the equation. And there's a nice result of Mireille Bousquet-Melou and Arnaud Gian from... yes?
By the way, what is your goal exactly? You want to address the algebraicity of the
So my goal is to show a strategy to prove the algebraicity of large step models, which is generic, which works for all algebraic...
Yeah, but I'm referring to whether it's the complete generating function.
Oh, okay. So you're asking if we, in testing, is a complete generating function or just the excursion, so generating function, for instance. Here, it will be the full generating function, qxy. So I go back to this result. So this theorem states that the solutions of equations in 1 catalytic variable are always algebraic. And moreover, this is an effective result, so that it gives you an effective way to compute the vanishing polynomial of the solutions. So we started from an equation in 2 catalytic variables, and we want to find equations in 1 catalytic variables for the specializations qx0 and q0 right, but only 1 variable each. And this is precisely the strategy that was devised for small step model in 21, and that was applied successfully, for instance, to prove the algebraicity of the Gessel model, which hadn't been done before. So I will now explain to you how the strategy works and what are its ingredients. And it relies on an object that are called the invariants, and they were first introduced by Tutt to study families of planar maps. So you start with some polynomial kxy, and you define a pair of invariants to be 2 power series in x and y, such that they are equal modulo kxy for a notion of modulo that I don't explain here. And they are really interesting because they give you equations. So if you have a pair of invariants and you can expand the following series in x and y and see that it has no pole at x equals 0 nor y equals 0, then you know that the pair of invariants is actually a pair of constant invariants. And so here, what you see, you have actually 2 equations. You have an equation I of x equals c of t, and an equation g of y equals c of t. And these will be our catalytic equations in 1 variable. So I'll show you an example of application. Basically, what we want to do, we have some pair of invariants I1, J1 that we don't know, but we only know its expansion at x and y. And we have another pair, I2, J2, and this one, we know fully these invariants, and we have these expansions. So what I can remark is, if I perform the following operation on I1, I get something in 1 over x2, which is precisely the expansion of the second pair. So what I do is I remove I2 to get something that is constant when x goes to 0. And so what I do is I perform the same operation on the 2 pairs, which gives me something that is constant in both coordinates. And I know that if I perform arithmetic operations on invariant, then I preserve the invariant property. Therefore, I have a pair I3, J3, which is defined as follows. That is a pair of rational invariants satisfying the invariance lemma. And so I have these 2 equations. Okay? Now I will show you how to express. Okay, so you have these 2 equations. Now, how do we exploit it to perform the algebraicity proof? Well, you start with our running model, and you remark that the right-hand side is almost of the form a of x plus b of y, except for this term, xy. So what we do, if we simply guess a pair of functions f of x and g of y, such that xy writes like this, modulo k. And now we reinject this identity into the functional equation, and we get a first pair of invariants that involves the functions a and b that we don't know. So I do as follows: I guess this pair, and then reinjecting it, I get a pair of invariants. And now, out of my hat, I get a pair of rational invariants that I know. Now, I look at their poles, and I see that if I'm clever, I can produce, like before, a pair I3J3 without poles. I succeed in doing so. I won't show you the exact computation because it's a bit ugly. And so I can apply the invariance lemma, which gives me I3 of x equals c of t, J3 of y equals c of t. And these are equations in 1 catalytic variables that involve q x0 and q0y. So now I apply the results of Bosquet-Melou and Jehan, which give me the algebraicity, and I reinject it into the equation, and boom, qxy is algebraic. One more time. So this time I take this model with large steps, and notice the exponents 7 and 2. They correspond to the fact that this time I don't start from the origin, I start from the point 7, 2. Okay? But basically the functional equation has the same shape. So I find a decoupling for my monomial here, which gives me a first pair of invariants. Now I guess a second pair of rational invariants. This one is a bit messier. I look at the poles and I perform the elimination, which gives me 2 pairs of rational invariants, 2 pairs of invariants without poles, giving me 2 equations in 1 catalytic variable, and it shows me the algebraicity of qxy. One last time. So in general, we focus on models which have small backward steps, okay, in order for the functional equation to look like this. I find a decoupling for the first monomial, giving me a first pair of invariants. I find a pair of rational invariants. I eliminate the poles between these 2 pairs of invariants, and therefore, I prove the algebraicity. So this proof, which is quite generic, relies on these 3 main invariants. So decoupling of a fraction in terms of f of x and g of y, 2 fractions, a pair of rational invariants, and the pole elimination. So what the authors did before when they devised this proof, they focused on the small steps model, and it was then quite simple to find decoupling, rational invariants, and pole elimination. But for larger steps, the theoretical tools didn't adapt verbatim. Hence, our contributions. So, if you start with some bivariate polynomial, you can associate it a graph, which is called in the literature the orbit of the walk. What we do is we endow this existing object with the action of 2 Galois groups, and the name. This relation between these Galois groups and these graph objects, this allows us to perform the first 2 points. Basically, we have the existence of non-constant rational invariant if and only if the graph is finite. Moreover, if the graph is finite, then the question of decoupling is a mere computation. And moreover, these two steps are not theoretical, they are effective, and it's poorly written in Sage. Maybe I can ask Frédéric. And using these two tools, we prove the algebraicity of these two models, which were the first one with large sets we proved algebraic. And moreover, we did the method of Bousquet-Mellot and Jehan to the end to find the vanishing polynomial for Q00 of degree 32, which proves a conjecture they did. And moreover, as the decoupling is quite easy, then we could find a family of models which extends the guess L1. So we stretch the right steps, and we conjecture that they are all algebraic for these starting points. So now, in the remaining time, I will try to explain to you how to compute the invariance and decoupling in case you are dealing with such equations. So I will present to you the orbit, which was defined in this paper. And the idea is to find nice pairs of changes of variables. So you start with the natural one xy, and you want to find pairs uv such that suv is constant equal to sxy, and moreover, you want to change only one coordinate at a time. So I will show you on an example, our running example. So I start from the pair xy and I fix the third variable, so I solve for y prime this equation. I find two solutions, and among them there is a trivial solution xy and another one x1 over xy, which gives me one new pair. Now I will perform the same step, but this time I fix the second variable and I solve the same kind of equation. This time I have three solutions, which give me two new pairs. And I do along. I continue with the new pair that I found x1 over xy that I found here, and so on. So this process, which is basically saturates the pairs, might not terminate. And we currently don't have a way to know whether it will terminate. However, in some cases, it does, like this one, and you get a finite graph. So the vertices are labeled by the pairs of variables. The variable z that we find there is a quadratic variable over cxy. That's why you have a branching point here. Okay? So, and moreover, z is enough to generate all the pairs of variables in this orbit. So, and also the edges are colored according to the variables that is changed. So, for instance, this one in red because the x didn't change. And now I can delve a bit into the construction. You take the field extension, which is generated by all the coordinates that appear in the orbit. It turns out that this extension is Galois over C of x and C of y, and it has two Galois groups, gx and gy. And these Galois groups, in turn, they act on the orbit as graph automorphisms. And this is this relation between the property of these Galois extensions and the graphic properties of the orbit that allows us to compute the invariance and decoupling. So this is how it's done. For rational invariance, we have this equivalence, that the orbit is finite if and only if there exists a pair of non-constant rational invariants. And how do we compute them in this case? Well, we are able to compute the vanishing polynomial of the less coordinates of the orbit as follows. And then it is reducible, and moreover, its coefficients, they are rational invariants. And now that we have computed it, it turns out that any non-constant coefficient of this polynomial generate the whole field of non-constant rational invariants. So I show you an example here for the running example. We compute these polynomials. You see that some terms, they are constant, t plus 1 over t, and some of them aren't. And moreover, as the coefficients are rational invariants, I can also express them modulo k in terms of y and t. And I simply take the coefficient of z5 to be my pair of rational invariants. Now I will talk about the decoupling side. So as the labels of the vertices are pairs of variables, it is natural to evaluate by variate fractions on them. And it is also natural to extend this evaluation by linearity. So I will show you an example here. If I want to find a nice linear combination which cancels pair of in the form f of x plus g of y, then I can simply find a bicolor cycle and put plus minus along it. Then, if I evaluate f of x on it, then you see that the terms, they telescope and you have 0. And the same goes for functions in terms of y. And therefore, we will construct this kind of pairs to characterize the decoupling of the fractions. And moreover, another example is this one. It turns out that the evaluation commutes with the action of the Galois groups. And therefore, if you find a chain, if you find linear combinations which is stable by the action of the group Gx, then Galois theory asserts that Hc is a function of x by Galois. So these are the two ingredients to build the following theorem. So we are able, when the orbit is finite, we are able to decompose the pair xy as a sum of 3 linear combinations whose roles are as follows. If h is in the form f of x plus g of y, then h alpha equals 0. And moreover, it is a characterization of this fact. And moreover, if f admits a decoupling, then the x and y components, they are given through a mere evaluation on these two linear combinations. So I show you how it is done for our running example. Here, I draw the orbit in 2 ways. And you see that I define some families of vertices called level lines. And these are the linear combinations that are sufficiently symmetric through the action of the Galois group in order to give me functions in f and y. And so I have a nice formula which expresses me xy in terms of these linear combinations. And hence, by evaluating the fraction xy on it, I obtain a function of x plus a function of y, modulo k, which is my decoupling. So I will finish my talk with some further questions. First, all that we did relied heavily on the fact that the orbit was finite. And so what I tried to do is to compute many orbits for various models in order to look for one finite orbit. And it is really hard because it requires to compute with resultants and all. It's a bit ugly. We want to find a way to decide the finiteness of the orbit, basically. Moreover, the first step I didn't explain is still done by hand, and it's not quite difficult, but I hope that it could be automated. And finally, we want to find new models on which apply the strategy. Thank you, everyone.
Are there any questions?
So thanks for the talk. In your equation for fx0, you had some derivative. And where this derivative come from is from the pole elimination step.
So I will explain a bit
because I think you didn't in the example.
So, okay, what you can do is if you have, sorry, I look for, sorry. Okay, if you have a catalytic variables equations, you notice that the C is not expressed in terms of the derivative of Q, but actually what you can do is show that the C is totally determined by Qx0. And this way you will express it in terms of the derivatives of Q at 0.
No, but my question is where does the derivative in this U come from? Because when you do this pole elimination, you use derivation.
It
is
comes
that correct?
From the fact that you need to expand the unknown invariants in terms of x. So to get more terms, you express them in terms of derivatives.
Thank you.
More questions? Okay, if not, let's thank the speaker again.